Okay, good morning, everyone. Thank you for that wonderful introduction. Again, I am Samantha Servo, and I will be talking about From Genes to Grids, how Python brings sequence alignment to life. All right. Okay, so I won't be delving into this because I was already introduced. Again, I am Samantha, and I am interested and passionate towards the intersection of tech and biology and medicine. Okay. For now, what we're going to cover are the following. First of all, I will be talking about the alignment problem, or what is sequence alignment, the global and local algorithm related to it. Secondly, I will be teaching you the intuitive process of the algorithm mentioned. And thirdly, I will show you how it is used in production. It's usually used with the BioPython library. And lastly, I will be talking about just summarizing everything that I've talked about. All right. First of all, I want to ask everyone here, how many of you ran Git diff this week? Or anyone who is familiar with this? Because I know a lot of people here are programmers. So can I see a number of hands that are familiar with this concept? Okay, that's nice. Okay. Actually, the Git diff algorithm, it uses the Myers diff algorithm, and later on, I will be talking about the mathematical foundation of it, which is from Levenstein's edit distance. I will be talking about that shortly, but I just want you to know that a variation of this idea of the edit distance is actually the Myers-Diff algorithm and the other algorithm that I will be talking about later, which is related to biology or bioinformatics. Okay, what are the common use cases of sequence alignment? Just so we know what are the practical applications of this. We have the cancer mutation detection for COVID variant tracking. So during the COVID pandemic, they also use sequence alignment to figure out the different variants, antibiotic resistance, and also for pharmacogenomics. So these are just the use cases of sequence alignment and why we should care, because we know that sequence alignment is, in an idea, it is aligning different DNA sequences, right? But it has a lot more impact than just aligning strings. Okay, I just want everyone here to know that sequence alignment algorithm didn't start originally with biology. Just like what I've mentioned earlier, the idea of Myers-Diff algorithm actually came from Levenstein's edit distance idea, and also the sequence alignment algorithm of Needle-Wunsch actually came from Levenstein's edit distance as well. So there are different variations of that idea, and now I will be talking about this concept of how we came to this algorithm that didn't start with biology. Okay, first of all, we have the Act of Levenstein in 1965. Levenstein is actually a linguistic. He's not a biologist or something. He is a linguistic with this question: how many single character edits, such as insertion, deletion, or substitution, does it take to turn one word into another? So how does that look? I have an example here. For example, we want to turn the word kitten into sitting, right? We want to turn this first word that we have into our target word, which is sitting. How are we going to do that? Of course, what we're going to do is to substitute some of the letters, right? First of all, in this word, we can substitute the letter K into letter S so that it will be similar, right? And checking the second, third, and fourth letters, they're just the same, so they will remain there. For letter E, we're going to substitute this with letter I, and this will remain here, and we have a gap here. Because this word, the kitten word, is only consisting of 1, 2, 3, 4, 5, 6 letters, while the target word is consisting of 7 letters. So what we just did here is turning the characters into the target characters. We're just editing the characters from the first word to be the same as the second word. So what does that mean? No, why is that important to us? It is important to us because this is similar to the idea of DNA sequencing, because we are doing insertions such as this, the letter G, or substitution in which we are changing a letter or a character into another. That is the basic idea of Levenstein. Next, we have Bellman. Now we're going to delve into dynamic programming part. It is actually developed for military use. And fun fact about this, the programming term here is not originally, it doesn't originally mean for programming context that we know right now, like for coding and stuff. It actually meant military program. That's the original idea there. So for this second one, the dynamic programming idea didn't come from the idea of coding initially. So it's actually in a different context as well. So as you can see, we are seeing the pattern here that what we are using here is not, the concept that we learn about this is not really originally from what we thought the context were. The knowledge were just transferable. And as you can see, it is originally used for the military use, yeah? And the third one, this is what we're going to be focusing on, the Needleman and Watch. Those two people are actually two scientists, biologists, and they are borrowing the idea of the edit distance from Levenshtein because their algorithm actually came from Levenshtein's edit distance. And they're also applying the dynamic programming because later I will be showing you how we can use the algorithm of Needleman and Wunsch, or let's just call it the global alignment algorithm in code. Okay, now that we know that the biology sequence alignment algorithms didn't actually come from biology itself. Like, they didn't wake up and think, okay, let's create an algorithm for biology. So you can see it is transformative. It actually came from every other ideas in other fields like linguistics, and then in a military field like that. And then it transformed, we got the idea and it transformed into something that is usable for biology. And I know everyone here knows already that DNA is a string. It is a sequence of 4 letters, A, T, G, C, and that's what we're going to focusing on. But I want you to take note as well that sequence doesn't mean it's always DNA, okay? There are protein sequences as well that we can align. However, those are 20 characters type of sequences. So for the interest of time, we will be focusing on DNA sequencing and just use 4 letters, okay? Then we have the global alignment here and the local alignment. These are the two main algorithms that are used for sequencing. We have the global alignment, the first one that I've talked about. It means that we are comparing the entire sequences from end to end. It just means that if you need to see the whole picture of the comparison of different sequences, you're going to be using the global alignment. For the local alignment, it's just looking for the best matching region within the longer sequences. It just means that you're already looking for a pattern in a sequence. So you don't need to see everything, compare everything, and have it 100% comparison. You just need to know the matching pattern that you're looking for. So imagine you're using the grep function, right? So you already have a pattern that you're looking for, and you can already locate it in the sequence. That's the difference of the global and the local alignment algorithms. For the global, it's end-to-end, and for local alignment, you're just looking for a specific thing, okay? Right, so now I'm going to teach you how we can intuitively understand the algorithm, how it really works manually. First of all, we're going to build the scoring grid. So this is the grid, and in this part, we have the match, mismatch, and gap. Those are the things, the concepts that we need to understand. And you can see there are numbers that are corresponding to each. +2 for match, -1 for mismatch, and -2 for gap. And these are the two sequences that I will be talking about. Now, we have settled them in the grid. We have the first sequence here on top, and we have the second sequence here. We are going to be focusing from this cell up until this bottom right cell, okay? Now, I'm going to show you how we can solve it. First of all, let's focus on this one. We have 3 neighboring cells here. The top cell, the cell diagonal to this cell, and the left cell. The first step is to compare the first letter to the second letter, okay? So if they are the same letters, what are we going to get? A match, okay? If these two are a match, we're going to add the value given here into the diagonal cell. If they are not a match, we're going to add this value. So the first thing that we're going to do is to focus on the diagonal side. For this, since they are a match, this is automatically plus 2, right? And for the top and left cells, you can always add the gap value. So we're going to add -2 here for the both sides, and we have -4, and +2, right? And within those three cells, what is the highest number? The diagonal, right? You will be choosing the highest number here in the three neighboring cells after you have computed them all. And that will give us the answer here. So since we know that 2 came from this, later I will be showing you that you have to be using traceback or using arrows in order to indicate where the answer came from. Let's do another one. It will be 0 because you're going to just compare this. It will be -1, add -1 here, we'll give -3, then add -2 for this 2. We'll have 0 here and -6 here, right? You're just going to do that for every cell, and then this is the arrow that I'm talking about because we got this answer from the diagonal cell, so we're going to point it from there. And this answer came from this because this is the highest number that we got after computing the three cells, so we're going to point that to this arrow, and so on and so forth, up until we finish that in the end. So this number, the bottom right, is actually the alignment score that you will get after computing this. This is just the scoring of the whole sequence that we have compared using the scoring values that we have. And I want you to take note that there are three different paths that we can see. You can call this as optimal alignment. So we have the first one coming from 0 down here, and this one in the red arrow path, and the purple path. So you can see that there are three possible optimal alignment because it just means that you can align the sequences in different ways. In this case, we can align them in three different ways because we have three optimal alignments that are resulting in this alignment score. And I want you to note that the optimal alignment and the score, the alignment score, is actually dependent on the type of value scoring that you will be using. This is just the default, and when you are looking for the number that you should be using for these three, it is actually dependent on the biologist on deciding what kind of context they are sequencing these sequences are and figuring out how they can use this. So now that we know the basic idea of this, it's easy, right? It's just interesting to see how it is solving cell by cell and using the neighboring cells, right? You're just comparing essentially and just putting different values there depending on the scoring values. And now I'm going to show you how we can translate that grid into Python. This is just a simple from scratch code. It means that it is not yet optimized. So I just made this so that I can explain the different steps on how it is related to the intuitive grid explanation that I've done earlier. So as you can see here on the top, this is the grid that I have just explained to you, and this is the output of this code. So if it is translated into Python, you can see that it is just similar here, and also the alignment score in the bottom right, right? It's just a similar thing, but faster, because we don't need to do this manually, especially if we have a million bases of the sequence, because in reality, we're not comparing just 4 letters with the sequence. So this actually helps us out. And okay, now I'm going to explain a bit for each step on how you can see the intuitive step that I've just taught you earlier. Okay, for the first one, this side is just it is just helping us to create the empty grid that I've shown you earlier. Then next, for this part, the gap penalties. As you can see, before we solve the grid, there are already numbers on the top and the bottom, right? The 0, then -2 up until -8, right? Those are just gap penalties if we're using the global alignment. So that is just the given spaces that you're going to put. Because we have -2 as our value scoring, right, for the gap scores. So we use that as the scoring to put the values there, like in -2, -4, diba? We just added -2 there along the the top and the side part. Okay, those are the edges that we're talking about. The 0, -2, negative. Like, just think of it as it is a set idea already in this algorithm, and you just need to focus on the solving part of the inner cells. Okay, next, this is this is the ano. You're going to move cell to cell because I've taught you earlier that we are moving from left to right, then top to bottom, right? We have to solve it cell to cell. That's just how it works here. And then in this part, we are questioning if the row character and the column character is a match or mismatch. This is what we've done earlier. Now we are comparing the row character to the column character. And then this is the part where we are doing the computation of the three candidates or the three neighboring cells. No? We are doing the diagonal. If it is a match or mismatch, we're going to add the respective value. If it is a gap, we know that it is a gap, the up and the left side cell, we're going to be adding the gap score that we've done. And lastly, as you can see here, it has the best alignment score because it's just a simple matrix that you can read. Okay, as you can see here, we just put the row and the column side here because essentially the best alignment score is just the bottom right cell, which is similarly on what we're doing here. Okay, but that is too much work, right? We have written a lot of code just to do the same thing. It's faster, yes, because we don't need to manually do it, but it's going to be slow if we're going to apply the big data or the real data there. So we have BioPython. BioPython actually has this, and you can use this usually in prod. And as you can see here in this part, you can just switch it up. Like, you don't need to create a whole function. You can just call this and use this. Like, add global as the word if you want to use the global algorithm, or local if you want to go into the local algorithm. Okay, you can see here, you can just switch between the Needleman full sequence, or the Smith-Waterman or best region, because this is easier, right? And also you can just add the match and mismatch scores here yourself, right? Okay, and for this one, this is the difference between what we've done earlier with the code that I've taught you, because it is just for teaching the steps, but this is actually the production use. In this case, we have two gap scores, because earlier I've only told about one gap score that we use, right? The -2. For this case, we have two gap scores, the -2 and -0.5. They are called a fine gap penalty. Later, I will be talking about what does that mean. And this is the same. We just have the alignment or the best score because it returns the similar as before. It just returns the alignment score. Okay, I will be explaining why we have different gap score here. Because this BioPython library is actually more accurate to use than what I've shown you earlier to teach the code. Because in this case, we are actually using the pairwise aligner. We're just calling it the library. It's already done for us. What we're going to do is just call it. And also, they are using the concept of open gap score and extend gap score because this has a biological context. Because when it comes to this example, so let's see, we have sequence 1 and sequence 2. For the sequence 1, we have A, C, then 4 Gs, T, and A. And if you're going to compare that to sequence 2, it has AC, then 4 lines. So we already know if it is a line, it is a gap, and T, A. Okay. If we're going to use the flat gap score or the previous that I've taught you, which only has one gap score, we're going to be doing the matches. So we're going to count the number of matching letters here. We have 1, 2, 3, 4. And if we have number 2 as the matching score, times that, and you will get 8. And then we're going to go to the gap position. We have 4 gaps here, as you can see. And with flat gap score, since we only have one gap score, we're going to be indicating that each gap position here is equating to -2. So it is more expensive because it is penalizing higher because you're assuming that each gap here is -2. That is for the flat gap score. If you're going to total this, you will get 0 as the alignment score. However, if you're going to follow this BioPython usage, you can see we have the open and extend gap score. Okay, we're starting the same here with the matches, and then you have the open gap position. It just means that the this is the gap position in which the gap started. And then for the succeeding gap up until this point, it's only negative zero point 0.5. So it is lesser penalizing because the idea here is biological, as I said, and it just means that they are treating this whole thing as one biological event in comparison to this. So this is more accurate because if you have this gap, you have this gap in biological context, they are just focusing on this as one event because this is a continuous event, right? So if this happened, this is just one event. But for this one, you're treating each as a separate event, which is inaccurate because when it comes to biology, we need to see this. If it is a continuous gap, I will be explaining later. If it is a continuous gap, it is just one event because it happened once, right? And it finished here at this point because it continues comparing it to the other sequence. That's why it is important that we follow what is here, what is used in production, and you can just assign this because this is penalizing too much, assuming that these things are separate events, when in reality they are one biological event because of the continuous, they're succeeding it to each other. So they are one event. So you can just penalize the open gap because this is more expensive. As you can see, it's negative 2. It is more penalizing because it is the start of the gap. And it already knows that this is the start of the gap. So for the remaining, they can just use the extend gap score. So that's the basic idea on why this BioPython library is more accurate to use if you're going to use it on real data. Because we need to consider these things as well, not only the numbers. We have to consider the biological context. Okay, and now for explaining this, the output of this is just a simple output. It has the target, which is the first sequence. And this part, it just shows you what it does. So as you can see here, we have the first sequence, then second sequence. This symbol, it just means that they are the same. They matches. For the dots here, it just means they're a mismatch. So you can see here, and again, it is a match. If you see a negative, it is a gap. And why do you think a gap is more costly? A gap is more costly because it is more costly to not have the two sequences at the same length. And as you can see, what I've told you earlier with the kitten, turning the kitten word into sitting, you have to use a gap, like a line, to indicate that you have to add another letter, right? It is more costly to have that, to have a gap, because you're going to add another, instead of just substituting things because they are a mismatch. So this is less penalizing than the gap. And next here, okay, that's just the second sequence, and the score, the alignment score. It's just in this format because it is the default of this library, so it's in this format. Because in reality, we're not only using whole numbers here, so there are other values here depending on the biologist or whoever is using this. Okay. Okay, now what we've learned about this is I want you to note these things. It is a simple algorithm and it has many uses, but I want you to know if you're going to understand his, we have different scoring values, okay? If we're going to use different values, as you can see earlier, when I compared the flat gap score with the affine gap score, so you can see the affine gap score gave a higher value, right? It's because with different scoring values or the basis of scoring used, you can have different optimal alignment and score. So it is entirely dependent on the scoring values that you've used. And also, yeah, we learned about the global and local. Yung local alignment algorithms, it's just a different kind, but I won't be able to show it because we're focusing on the global alignment. It's just, it is similar in a sense because it has the grid as well. The local alignment has the grid as well, but it starts with 0, and it always has 0 in its choice when we are solving each cell. So it's just similar in a sense with the global alignment, but different usage. And this is the intuitive three-step global alignment algorithm that I've taught you. So uh, it's just starting with creating the grid, comparing the row characters to column characters, adding match or mismatch value to the diagonal cell, then you will add the gap values, then get the highest from the tree. That is the main thing that we're doing here in this algorithm. Okay. Okay. Again, this I showed you earlier that there are multiple paths or multiple optimal alignments with similar score. They are similar scores because we have used similar value scoring there. Huh? That's why they're all pointing to the alignment score of 2 with different optimal or different paths because it's just the same scoring value. And next, oh yeah, right, I showed you about the global alignment algorithm with Python. So that's all. I've talked about mainly what is about the sequence alignment on the use cases and also how the algorithm works intuitively and how BioPython can actually use it to how we can use BioPython to make it easier for us to apply this in a faster way. So yun. Thank you again. Thank you for listening. I am Samantha Servo, and I hope I've sparked interest for bioinformatics. Thank you.
Okay, we have room for two more questions. Does anyone have any questions for the speaker? Feel free to approach the mic and ask the speaker your question.
Hello po. I'm John Kevin Braga, a math student. I've noticed that in your section 2,
Yeah.
it was indicated there that you add a gap score on both
Yeah.
insertion and deletion.
Yes.
Is it possible that in some fields of biology, insertion or deletion might be more expensive than the other? And the second question is, if there's a chance for transpositions to be indicated in the algorithm, since it's possible that two characters are just swapped, and it might
Yes.
be cheaper if we could just swap them instead of inserting and then deleting.
Yeah. Okay, for the first question, yes, it actually depends on the biologist or the scientist to figure out what scoring value that they're going to use. The scoring value that I've shown earlier, the value of positive 2 for match, negative 1 for mismatch, and negative 2 for gap, they're actually just the default and they're not used universally. So it depends on the biologist or scientist on how they're going to score it in the context of whatever they're using the sequencing for. There are actually another example for this. Kasi DNA sequencing is not just DNA, no? The sequencing, it can also be protein sequencing. For protein sequencing, they have actually the Blossom 62, if I'm not mistaken. That is the scoring value that they use universally for protein sequencing. So there are other universal or standard conventions for scoring values for other like proteins, but for DNA, I think it depends more on the biologists. They are the ones with the context and they will be deciding on how much they're going to penalize the change. And for the second one, if I'm not mistaken, the question is why can't they just swap, right? Okay, so it depends. It actually depends always in the biologist. But in this case, because we are comparing sequences, right? Different sequences. There are times that you will be needing to insert or delete something. There are always instances, not always, but there are instances like that. If you're going to compare two sequences, if they're not, let's say they're not in similar lengths, you're always going to have to insert something. And there are times that when we are doing this sequencing, no, it is actually called the polymerase function. The polymerase function is the copying function. You can just imagine it as copying function. There are times that it will slip. So when it comparing two sequences, it will skip some of the sequences. So that will render us, giving us the gap. That's why I talk about the affine gap score. So the opening or the starting gap score, which is we referred to as open gap, it is more expensive because it started the gap. And then the continuing gaps, the following gaps from that open gap, it's called the extend gap because it is one biological event. That's what I'm talking about because we can't penalize each if it is happening only once. That is what's happening behind. So there are really times that we need to do that because the polymerase function, the protein sometimes slips up. So there are times. And there are times for real data, it's actually kind of rare to see a perfect sequence in reality. So we are bound to experience that or encounter that. So yeah, it depends on whatever sequence that you have. Actually, thank you for the question. Yeah, hopefully I answered your questions.